Welcome to a video that will cover how to do the labs in this course. This is a full walkthrough that's going to go through how to understand what the lab is about, how to collect the data, and how to create the lab report. By the end of this video, you'll have everything you need to know to do the rest of the lab projects and reports throughout the rest of the course. So let's get started. Let's get started by going to D2L. This is the D2L homepage, and we need to begin by finding the resources for this lab. They're under the content section. This is going to be a demonstration, but I'm going to do it with a real lab that you will eventually have to perform. So let's do Lab 1 FreeFall. Now you can see the familiar structure that our labs will have. There is going to be an instructions document as a PDF, a link to the Pivot Interactives page. This is where you'll find the video from which you'll collect data. Then there's going to be a Word document that is the lab report template. This is the template that you have to fill out for your lab report. Finally, there's going to be a link here to the D2L assignment Dropbox, where you'll upload the PDF of the completed template. Let's hit them in order, beginning with the lab instructions. If you want, you can download this file by clicking here. Each of these files, the one for each lab, will have a similar structure. There's a Getting Started section with an outline of the tasks. There is an introduction section explaining what the lab is about, what the variables involved are, and how to do the curve fitting. There's a reminder of the plotting standards, and then a reminder about what to do if you're having trouble. So the main thing we need to review is the outline of the structure of the labs here in the Getting Started, and then also an overview of this particular lab's introduction page. So on the Getting Started page, we have the first step is to watch videos, and there are a variety of videos available. The procedure video is the short video clip that will explain to you how to collect data for each lab, as well as give an overview of what the lab's about. The experiment video can be found on Pivot. That's the one you collect data from off screen, or on screen. And the last part is the Plotly instructional video. This is a separate video on D2L about how to use the Plotly Chart Studio software for making plots and storing data. The second aspect here is analysis in Plotly Chart Studio. General procedure is create a data table, record data from the video and fill in that data table, use the data table to make a plot, and then eventually do the curve fitting. Third section is to do calculations. Once you have the curve fit parameters, the numbers that make the mathematical equation match the data, those curve fit parameters can go into a separate equation, which will be given to you in the lab, from which you can actually compute real world physical quantities like mass or length. Once you have that real world quantity, you can compare it with its accepted value and compute a percent error for the lab. On to section 4, the lab reports. I'm recommending that everybody complete the lab report using Google Docs, but the first step is to come here to D2L and download the lab report template and then upload that template into Google Docs. I chose to do it this way rather than sharing a Google Docs link directly. Next, you need to basically fill in the template. So paste in data, paste in your plots, and complete the written responses. And then the last step is simply to download the PDF from Google Docs. So take your lab report and there's an option for export PDF, and then that is what gets uploaded here on D2L in the assignments Dropbox. Let's start talking about what this FreeFall lab is all about. So basically, we are trying to measure the acceleration of a ball during freefall. Remember, acceleration is not the same as velocity. Acceleration is the rate that the velocity is changing, how fast it's speeding up when it's falling, for example. The acceleration of any object in ideal circumstances would be 9.81 meters per second squared here on Earth's surface. We'll see if we can get a close value to that based on our data in this lab. So I have some background information here. Free fall is basically a type of motion where, as it says here, the only force acting is gravity. So there's nothing else. We're not considering air resistance, and you don't include the force that made the object move in the beginning. A fun fact is that freefall actually describes both the upwards and downwards path of an object that's thrown in the air. So as soon as a thrown object, let's say, leaves your hand, it actually enters freefall, because the only thing pulling it down is gravity, even if at the moment it has an upward velocity. You could also say that the moon is in free fall around the Earth because the only thing affecting its motion is gravity pulling it towards the Earth. Okay, so the variables we're interested in here are the vertical position of an object that was thrown in the air and the time that has elapsed, the current time. Our plan is simply to measure position and time for several points while an object is undergoing free fall. This is the kinematic equation from physics, classical mechanics, that governs this behavior. Basically, y is the instantaneous position, t is the time, and this equation allows you to predict the position of an object at any point in time. However, it requires three parameters: g, the acceleration due to gravity, v1 is initial velocity, and y1 is initial position. We can re-express that equation in a generic way here, where all the variables have been mapped over. Y went to y, t went to x, v1 went to b, y1 went to c, and this combination of -1/2 g went to a. You can then use that relationship to solve for g in terms of these abstract variables, and that's exactly what we have here, g equals -2a. So our procedure is to measure position and time data points in the table, plot them, perform quadratic curve fitting, and let the software determine what is the a, b, and c that matches the data. -2 times its value of a will actually be the gravity acceleration that we can then compare to 9.8 and thus validate our model and complete the goal of our experiment. Here's a quick review of the plotting standards. So this is what a plot should look like, a nice professional, easy to read plot. Notice that it has a caption describing what it is, especially useful to a person who had not seen the data before. We have a clearly labeled X and Y axis with units. All the font is large and readable, and I'll specify down here, font should be at least 30 pixels in size. The pixel dimensions of the image should be 1200 by 800. And on the report page, the image should span at least about 5 inches, which is what you see here. Axes do not have to go through the origin, but they should be trimmed so that there's no empty space on the axes. This large empty space is fine, it's just the way the graph looks, but there's no extra space here on large x values, and we don't include the origin on the x-axis. We actually stopped here at 0.05 because that would just introduce unnecessary white space. The extra white space makes it harder to see the true shape of the data. You can read the rest of these details on your own. Let's move on to the troubleshooting. One of the big themes I have in this course is this is supposed to be fun. This is the exploration of the principles of the universe. I hope that you find time to work on this project, but also keep a certain relaxation and positive attitude about it. So with that in mind, look at these as challenges, give it your best effort. As long as you're making a clear, demonstrable effort, that will be reflected in the grading. Of course, nobody likes to get a low grade, so your two options for getting help is to actually ask other students on the D2L discussion board. This can be especially useful for the challenge question in each lab report. The other option is to just email the professor directly. I'm not a professor that likes to stand off in a distance. I like to be right there helping all the students. So all I ask is when you email me about a lab, please identify who you are, give the name of the lab, make the question as specific as possible. This is extremely important, guys. The more specific you are, the better the answer I can give you. And then also, extremely important as well, attach some evidence that you have already tried to make an effort to solve the problem. The only type of question that you can send me that won't get a nice, helpful response is something along the lines of, "Hi professor, what do I do? Hi professor, I'm not sure how to start." You need to make some effort to get started and to make progress before it's a worthwhile idea to email the professor and start getting extra help. Okay, so that is a rundown of the instructions for this lab. The next thing we need to do is try to start collecting our data. Remember, we need to get our position and time data as specified here. Alright, so back to the Lab 1 folder. When I click this link, I'll go to the Pivot website, and now we can see the video pane that has the information from which we'll get our data. So we have some bullet points here to go through. The video below shows 5 spheres tossed upwards and falling back down. If I scroll through the video here, you can see that that's exactly what they're doing. Okay. The masses and diameters are shown. If you go to one of the earlier frames right here, you can see the name of all the objects and their mass and diameter is given. The frame that shows the exact moment when the spheres are at the top is labeled top. I want to point out here that in addition to sliding back and forth here with this control, you can also use the keyboard keys. And that can be useful for finding precise positions. So if I find a precise position here, I can find the frame that's labeled top. Okay, and now we need to use on-screen tools to measure position and time. So this button over here activates the on-screen tools. We can get vertical rulers like this, and we can get a stopwatch. This stopwatch has one button in the middle of it, and the right side of it actually, that can reset the time to 0. So the idea is to just start the video at some position where the ball is not touching the person's hand, so it's in free fall. I can position it right here, let's say at -50 centimeters, restart my timer so that my timer is starting from 0, and so my first data point would be -50 centimeters and 0.00 seconds. Alright, so we're ready to start collecting data, and what I'd recommend you do is head over to Plotly Chart Studio to start entering it. Let's go back to D2L, back to the Lab 1 folder, and just to save you some time, I've put the link for where the Plotly Chart Studio is located. This link here, which I'm not going to click now, is a tutorial video just for Plotly Chart Studio, but right now this one below it will take us to the actual site. Sign in. And on the left you can create a new chart. New chart. Okay, so this is the main Plotly window. Let's start entering data. I'm going to go ahead and use my Windows 10 feature here to split the screen into 2 parts. So I can have the video on one side and the data table on the other. And also, I'm going to rename my headers here. So I have A and B and C. I'm going to rename A using that small drop down. I'm going to rename this time in seconds. B is going to be renamed as vertical position in centimeters. And then this is going to be column C is vertical position in meters. It's very important, guys, whenever you're collecting data, to always have columns that represent the raw data. Never do an on-the-fly conversion. Always do your conversions later, so you can always fall back on the raw data in case the conversions were done incorrectly. If you do the conversions on the fly and you make a mistake, you lose some confidence as to what was the actual original number prior to the incorrect conversion. Okay, also, this is not Excel, so I won't be able to do these conversions using a formula. I could do them in Excel or in Google Sheets and paste it back, but I'm going to be doing everything manually here. So it's time to start entering data. Here comes 0.000 seconds. You should establish a consistent number of decimal places. Here I have -50.0 centimeters. Okay, I'm going to do every 10 centimeters here. So I'm going to do -40.0, -30.0, -20.0, and onwards. Okay, so there they all are. I could also go ahead and do the vertical positions now, if I wanted to. Okay, so there's all the positions, and now we have to go to each one of these and measure the time. So let's advance the video here on the left-hand side to when the ball is just approaching the 40. I like to go above it and then use the arrow keys on the keyboard to bring it down just to the line, till the gap disappears. So here we have 0.034. Advance the video till it's above the line, arrow key down to the line. 0.72. I'll point out that in future videos, I'm not going to do this all the time. It's going to be up to you to collect your own data. I'm doing it here. The first one is a demonstration. For this one, I'm going to keep scrolling around until I find the one that exactly says top. Okay, so that was the most labor-intensive part of this process. We now have all our time in position. It's time to add a trace. There's our initial plot. A parabola is expected. Let's go ahead and add the curve fitting. Actually, striking that, there is one thing we should do first, and that is to click Save right now. As I noted in the one unusual part of Plotly is that you can't save it if you've added advanced curve fitting. It won't matter in this case because we're using basic curve fitting, but it's a good habit to get into. So let's save right away. FreeFall plot, FreeFall data. Set both of them as public because why not? And save. Okay. So now we should add in some x-axis, time in seconds, y-axis, vertical position in meters. I'm going to go to the Style tab and change the font size to 30. This is going to help when we're later exporting. And under Analyze, I'm going to go Curve Fitting, add a fit up here at this Fit button. And then under Basic, let's just use a quadratic fit and hit Run. Alright, visually it looks pretty good. And now we have our parameter A. I'm going to go over here and just record some data. So we have a theoretical g, acceleration due to gravity, that's 9.81. Our experimental g is going to be 2 times this value. Which is 9.83. Not too bad. And then finally, we can do a percent error. The percent error is simply the difference between these numbers divided by the theoretical. So I'm just going to do that here in the calculator explicitly for everyone to see. 9.83 minus 9.81 is of course 0.02, and then divide that by theoretical. So divide by 9.81, and then multiply by 100. And so our percent error is actually 0.2%. That's very good. So the analysis is done, the plot is made. The last thing we need to do here is simply export this as an image file. So I'm going to click export here on the left, image, custom size, and I already have it set for 1200 by 800 pixels. So let's download that, and it'll go to my browser's download folder. I'll save one more time, and then we can close. Well, we still need our values here, so I guess I'll leave Plotly open, and let's just bring it back into the main window. Okay. All right, so if we check out our downloads folder, we now have that undefined. That was actually the image that we just created, and here's our image of the plot, looking quite parabolic. I'm back in D2L, and I'm going to go back into the lab folder to see what I have to do next. I've already followed all the instructions. I've collected my data from Pivot. The next thing to do is the lab report template. Here's how it looks. It has introduction, hypothesis, data table, data plot, and then 3 discussion questions. The first 2 discussion questions are pretty standard for every lab. The third one is a special challenge. More on that later. Right now, I need to edit this, so I got to download it to my computer. And then I'm recommending to everyone to either edit this file locally using Microsoft Word, or upload it to Google Drive and work on it further from there. So let's do that. I've created a temp folder to work on for this. So I'm in my Google Drive. I'm going to click New in this top left and do File Upload. There I'll select the FreeFall Lab Report template that I had just downloaded from D2L. This is a docx file. Now that it's uploaded in my Google Drive, I can open it with Google Docs. To do that, just double click it, and then at the top click Open with Google Docs. Just to avoid any problems, let's start by saving a copy of this file. And I can do that by going File, Make a Copy. It's also going to go into that temps folder we were just in, and I'll just put an underscore KFD to let myself know that this is the one I've edited. Alright, so now we're ready to start working on our lab report. Let's begin with, what are we testing in this experiment? To answer that question, we can go back to the goal statement in the lab report instructions. I'm back in D2L. In my Lab 1 folder, I'll go to those instructions. So I see my goal was to measure the acceleration of the ball during free fall. In a way, that is a goal, but it's not exactly an answer to the question of what are we testing. Stating your goal is not the same as what are we testing. So what we're trying to test is whether or not the acceleration that we measure is the same as Earth's acceleration. And you could write essentially that. If you want to write powers like this, you could put the _2. Another option is to select the 2 in Google Docs here and do Control period, and that will actually make it a superscript. So we're trying to see if our experimental value of the acceleration due to gravity matches the accepted value. That's what we're testing. You could also add, for more flavor, we are also trying to validate our model for linear motion with acceleration. So in some sense, the fact that our linear model, our model for linear motion with acceleration matched the data so well is in a way another thing that we're testing. We were trying to test to see if this equation would match the data. So that's a secondary test here. Okay, so what was our hypothesis? This is very simple. Our hypothesis was simply we expected the experimental value of acceleration for a freely falling object to match the accepted value. That may seem somewhat obvious and flowing from the original statement, but there are some cases where we're trying to test something and maybe we'd expect it to be the opposite because of some aspect of the experiment we're changing. So this is just to kind of nail down, even if it's obvious, what is it that we're actually trying to do here in this experiment. Don't be afraid to just give a one-line sentence like this if you can capture the essence of what the answer is. However, one thing to watch out for both of these is avoid trying to do a description of the procedure. Some people say, what's the point of this lab? What are we testing? And the answer is, we're trying to test to see if we can log into D2L, download a file, collect some data, make the plot, do everything Professor Dockwell asked of us. And that's of course kind of like a procedure, but it's not the the goal of the test objective of the experiment. Time to start copying some data into the data table. I'll always give you the correct columns here, but they might not be all the same columns you have in your own data table. This is just the final condensed view. The data values went in, but there's some border color changes. We can deal with that in just a moment. Okay, now that all the data is in, if you want to fix those borders, select everything, and over here under border color, just change it back to some shade of gray, like it was before. Next, for the data plot, click and delete the placeholder, and we're going to go on hit the menu to insert image and upload from computer. Our image was previously called undefined. Let's go ahead and call that FreeFall plot. I've now renamed the image, and now I'm going to select that renamed image and insert that into the Google Sheet. This is much too large, although it is nice and crisp and high quality. Let's decrease the size to 5 inches, as in our plotting standards. And it's looking pretty good. Next up is a caption describing to somebody who's never seen this plot before what exactly it contains. This is a plot of vertical position versus time for an object in freefall. There is a quadratic curve fit that agrees well with the data. Okay. One other thing that should be done that I overlooked is when we are making the plot, it's also a good idea to change these generic trace 0 and fit of trace 0 to something more meaningful. So going back to Plotly 1 second, you can just simply double click them, and I like to call this one experimental data. And then instead of fit of experimental data, we can do quadratic fit. Okay, I'm going to download the image again. It's called undefined again. That's okay. let me just copy the name of the one we just did. I'm going to delete that file and then rename the undefined again. Back into the template, let's delete the image and then reinsert the one that we just resaved. There we go. Back to 5 inches, and we'll be ready to move on. The last part is the discussion questions. So, accuracy is an extremely important section because this is basically where I'm asking you to report in about what you were able to extract from this plotting. Remember, we do the plot so that we can curve fit, and we curve fit so that we can extract a physical variable. What's the physical variable we're extracting here? Let's remember that we're after this g. It's the acceleration due to gravity, and it came from doing 2 times the a parameter of the curve fitting. So that is the experimental value that I want to check if it agrees with the theory. And so really, this paragraph comes down to basically giving 3 numbers. And they're the 3 numbers we had over here. The theoretical, the experimental for our parameter of interest, which is acceleration, and then the percent error. Put those into 2 sentences, and we're done with this question. Okay, that's all you have to do. This question is basically just a way for you to actually report into me what these values were. Now the next question is about error analysis. This is a very important part, and although we're not doing it in a fully rigorous quantitative way, it's an important thing to think about anytime you collect a value. I asked you here for percent error, and 0.02% seems pretty low, but you know, pretty low is a very relative measure. Is 9.83 sufficiently close to 9.81 that we can agree that our theory was correct at matching the data? Who knows? Is a difference of 0.02 meters per second squared a lot, or is that a little? You can't answer these questions unless you use a full error analysis approach. The basic idea is this. This number, 9.83, came from doing data fitting, and that data fitting came from a plot, and that plot came from a table of values. So ultimately, there is going to be an uncertainty on this 9.83 meters per second. There is a plus or minus something that is on this value. Maybe plus or minus, right now, we would like it to be 0.02 meters per second squared. That would be really nice if that was the uncertainty on this value, because if it was, that means that this range, 9.83 plus or minus that 0.02, would include the theoretical value. And we would say that we're as close to the theoretical value as we can be, given that our data has some error in it. But we're not going to cover in this course how to generate this kind of error estimate on our extracted parameter. It would be called the standard error of the fitting parameter after we converted it into this actual acceleration value. But we're not going down that road. What I want you to do is just think about this process, though, qualitatively. So what was the most significant source of error in this experiment? That is going to be, most likely, estimating the position of the ball on the screen as we're scrolling through the video. So I'm going to say, in full sentences, the most significant source of error was estimating, let's say measuring the vertical position of the balls. In fact, I'm actually going to go back to that 1 second because I want to show you something important about that. Whenever you take a measurement, guys, the measurement always has an uncertainty associated with it. And that uncertainty could come from anything. It could be because, you know, the table's shaking. It could be because, you know, there's temperature fluctuations. But the big one that's always there is your measuring tool has limited precision. If we think about this display, we have 40 centimeters going to 50 centimeters. Each one of these tick marks is 1 centimeter. So the most you could possibly be off if you did a competent measurement of, you know, here, where is the bottom of this ball? The most you could be off is by 1 tick mark, which is 1 centimeter. And if you give yourself a little bit more, acknowledgement, you could probably get it to about half a centimeter, half of a tick mark. So keep that in your mind, guys. Whenever you measure something, your measurement always has an implicit uncertainty of a maximum of half of a tick mark, because that's the most you could most likely be off by in the worst case. So that's what we have to do here. Our most significant source of error was the measuring the vertical position of the balls, and to estimate a numerical value, we're going to go with half a tick mark. So we could say that the vertical position measurements have, the technical term is an estimated uncertainty of half of a tick mark. A tick mark was 1 centimeter, so we're going to say 0.5 centimeters. Okay, now the last part is just really qualitative. Explain whether you think this can explain the main source of error. This is just kind of a time to reflect on your overall percent error. So normally we would check to see, we would do an error propagation, more complicated procedure. Here what I want you basically to do is just reflect on whether or not this number is high or low. If this number is very low, the percent error is very low, then most likely whatever error we had, whatever our most significant error we had, that's what's basically causing this. You know, but if our error was very high, then it's possible that whatever, even this most significant source of error might not really be accounting for it. So this is just kind of a little reflection, you know, based on how the experiment went. Do you think that whatever error you're quoting here is explaining all the error that there is, or do you think that there's some error that you're not mentioning here that is affecting this? So to give you an example of when this would not just be, you know, a trivial, yes, I think it explains it, there are some experiments where the model that we have will not fully fit the data. There will be some part of the experiment that was conducted in such a way, because of some real world complexity, that the model only aligns with part of it, and then there's part of the data that's not modeled by that equation. In that case, we could say that, you know, we think there are some sources of error between the data and the model that is more than just due to, you know, random measurement errors here that we're quoting. That there's, you know, some more error there because of, let's say, the imperfections of the model, or equivalently the real world complexities of the data collection. So just letting you know that most of the time this is just going to be a simple, you know, yeah, my error was low, I'm pretty sure this explains it, but it is possible for, you know, to get the opposite answer. So we can just say, it seems likely that the total error, that the overall error in the experiment was dominated by vertical position error. All right. So the last one is a challenge question. It's talking about air resistance. Do all objects fall with the same acceleration in the same gravitational field? And the answer is yes, if there's no air resistance. In our experiment, we investigated only one of the objects shown in the video. So remember, there was 5 different objects here. We only looked at the middle one. But it can be proven in the absence of air resistance that all freely falling objects accelerate at the same rate. That happens because heavier objects have more weight, more force pulling them down. You'd think they'd fall faster, but they don't, because they're inherently more sluggish and slow to accelerate. And so the two effects cancel out, and the objects, it tends to be that all objects will have the same acceleration. When there's air resistance, though, that goes out of the picture. And so we wanted to basically look now to see the effect of air resistance on the acceleration of these falling objects, and see if we can explain why air resistance might affect some objects more than others. So if we come here and inspect it, we can see that, at the highest frame, all the objects were lined up with this bottom, with the 0 centimeter line. But as they fall, let's go towards the end of the video, you can see down here, as they approach the -70 line, at least as this large steel ball approaches the -70 line, that this small ball and this green one are not yet at the line. They actually are lagging behind, presumably because of air resistance. Now some people might say, well, maybe air resistance is because of the size of the object. It's kind of like, pushing the air out of the way. The bigger you are, the more air you push. But that doesn't seem to explain how the large steel ball and the small steel ball are both falling at pretty much the same acceleration. So the only option left is it must be the material that these are made out of. And if you go back to the beginning of the video, you can see, where is it, that the two that are lagging behind are not metal. Metal is nice and smooth. It's kind of like a low friction surface with the air, friction with the air, whereas styrofoam is rough and it's got little air pockets for the air to go in and out of, and rubber is just generally a high friction surface because of the way that the chemical bonds are on its surface. So how can we condense all that into an answer? We would say here that not all of the falling objects appear to have the same acceleration. This is probably because of air resistance. You could say one might think that object size would control air resistance, but the similar acceleration for the large and small steel ball is not consistent with it. It seems that the composition of the ball, steel, rubber, and foam, has a more significant effect on the free fall acceleration. Okay, so that's all you need to put. Now, I recognize that this is probably a challenging question to answer, especially for students of introductory physics, but that's why it's a challenge question. If you think about it, the rest of this procedure, guys, is going to become very routine for you. Collecting the data, making the plot, doing the curve fitting, especially since I'm telling you, exactly how to do that in the instructions. The accuracy is just, comparing the fit, one of the fit parameters with the theoretical. Error analysis is basically just telling me about the tick marks, the most significant tick mark, essentially. The challenge question is the one part that's not just straightforward. And to answer this question, I have a couple of different pieces of advice. One is, please reach out to the other students in the discussion board. I think it would be fine if this was being discussed there. Another option is to just search online for information. This is asking you to talk about what affects air resistance. So you could just Google what affects air resistance. And the final option, guys, if you get stuck, you can always ask me, and I can give you some hint for that. But please do try to put some effort into this, and know that even if you don't get the same answer, even if you're looking at this and thinking there's no way I would have typed the same thing as the professor, that's okay. I'm just looking for a reasonable argument, and I can give you your credit that way. Okay, so we've completed the lab report. The last step is to save this as a PDF and then submit it on D2L. So let's go File, very important, File, Download, and PDF. I can't emphasize this enough, guys. I want PDF version of this document. Okay. So if we go to the Downloads folder, we can now find that PDF here on my local computer. Let's now close down. Let's see, we can get rid of Plotly and close down Pivot. Let's just go back to D2L, and the last link here in the folder, it looks like my PDF program just opened it up. The last link here in the D2L is a link to the assignment. So click that. Click Upload, and select the file that we just worked on. Notice that you must select the one that's .pdf that we just did. Don't upload the template, which will be blank. You could write a little cute message here if you want. Okay, it's submitted. You should get a confirmation email that it has been submitted. And one thing I always like to do is go back to the assignments tab here at the top, go find the assignment that was just submitted, and then make sure it's actually submitted. It says here 2 submission files because of just some other testing that I was doing, but normally yours would say 1. On that note, you actually can submit more than once, and the system only keeps the last one. So feel free to override your previous submissions if you'd like to. And here it is. We can even click on it. It's always a good practice, and just make sure that it's actually the correct file. And there it is. So, this was a complete walkthrough of how to complete the FreeFall Lab. I hope this was useful to you, and I hope that you will use this as an example to complete the rest of the labs in the course, since it's going to follow pretty much the same structure. In future labs, there will be a short video just giving some introduction to what's the lab about and any peculiarities and how to collect the data from the Pivot video. But as far as completing the template, answering those types of questions, this is going to be your exemplar. So thanks again for watching, and good luck on your labs.